Okay, so and as it turns out, these wave functions, these eigenfunctions, the psi NLMs, we have three quantum numbers here. So these the eigenfunctions are, each eigenfunction is uniquely designated by these three different quantum numbers, n, l, and m. Remember, m can go from minus l to plus l in integer steps. L can go from 0 to n minus 1, and n can go from 1 to infinity. Okay, so these psi NLMs constitute an orthonormal basis set, which means that they're orthogonal, and any arbitrary wave function can be expressed as a superposition of these eigenfunctions, just like we saw, for example, in the harmonic oscillator eigenfunctions, the infinite square well eigenfunctions, etc. And something that's very important is that for the hydrogen atom, all of the functions that have the same value of the principal quantum number n have the same energy, E sub n. Okay, so if we look back at the energy expression, okay, we see that the energy does not depend on any of the quantum numbers besides n. It doesn't depend on L, doesn't depend on m. Okay, and this lack of dependence, this is in general not true. Okay, so that is this. We remember that these are the energy eigenfunctions for this particular potential energy function. Okay, for any other central force potential, okay, that is not simply 1 over r with a constant, will not be, the energy eigenfunctions, the energy eigenvalues will not be independent of the other quantum numbers in general. Okay, so it's an accident. This is an accident that the accidental in the sense that only for this potential, only for the 1 over r potential, do you get the energy eigenvalues that are independent of 2 of the 3 quantum numbers. Okay, any other potential will show it will actually have a dependence. The energy eigenvalues will have a dependence on L and maybe m. Okay, for example, if you have if you have a Coulomb potential, but you have more than one electron in that Coulomb potential, okay, then what happens is that the various electrons screen each other. They modify the 1 over r potential to the nucleus slightly, and then you will find that the energy eigenvalues depend to some degree or another on the other quantum numbers, L and m. Okay, and so only for the hydrogen atom do we find this accident. Okay, you can also lift the degeneracy, as we'll see. We can also cause the energy eigenvalues to be dependent on L or m or both, if by applying an electric or a magnetic field. Okay, so we're used to thinking in chemistry how the different orbitals, so we have a principal quantum number, and then we have these different orbitals such as s and p, and they have different energies, and that in general is true. It's just only not true for the hydrogen atom. Okay, and so let's end our lecture today just by talking about degeneracy in the hydrogen atom. So as we'll see, the degeneracy in the hydrogen atom states, that is the number of states that have the same energy, because the energy eigenvalues do not depend on L or m and only depend on n, then there's but we know that we have more than one state for each. We can have more than one state for each principal quantum number n, because again, L can go from 0 up to n minus 1, and m can go from minus L to plus L in unit steps. And so we know that we should have some degeneracy because those will all have the same energy.